Hello again, everyone. Welcome to our discussion of section 1.5, where we will talk about solving equations, solving a few word problems, and we will also talk about function zeros. Function zeros are basically, just to give you an idea about what it is any x value, any value of the independent variable in an equation that makes that equation or function equal to 0, that is called a zero of a function. Okay, so we will be talking about these various topics. Before we dig deep into the details of that, I want to remind you to please skim through the section 1.5 from your textbook, if you haven't already, before watching this video, or before attending the lecture on this section or on these topics. After that, watch the video and attend the class and take notes of any questions you might have as I go over the material, or anything, take note of anything that you think might be important as we move forward. Anything that it's important to you. Okay? And then number 3, review your lecture notes and look back at the problems that you skimmed through in your textbook and redo all those problems. The problems you saw in the textbook, the solved ones, not the ones at the back of the section, the solved problems in the book, and the problems I solve here in the lecture video. And without looking at the solutions, try to solve those problems on your own without looking at the solutions. Okay? And then complete all the homework assignments by the due date. And of course, review all the previous material, which when I say review the previous material, I mean even half an hour a week would suffice. Because as we cover every material, and if you spend half an hour each subsequent week to review this material, everything is going to stay fresh in your mind. So reviewing it again the next time will take half an hour or less. Okay, that being the idea that to keep every material fresh in your mind, so that you can ace this course moving forward. Okay. So when we solve linear equations, by solving any variable, that word means that we want to isolate the variable. Okay, so you might have an equation with more than one variable, 2, 3 variables. The one variable you're solving for is the variable you are going to have to isolate. Okay, that's what it means to solve for a variable. So for example, before we look at this example, some of the equations, I don't like to give trick questions on my exams. So I would never give questions like this, which have, this equation has no solution. I would never give a question like this on an exam I design, but your online homework and the textbook itself might have problems that fall into this category. So just watch out for those problems in the textbook and in the online homework assignments. But I would never give something like that on an exam. Okay? So solve the following equations. Please pause the video, solve these problems on your own, and on the first page you have A, B, C, and D. So you have 4 problems on the front page. Solve those and then come back to video and see how your solution compares with mine. Okay, I'm assuming you've done that and now you're back. So going back to the idea that solving means isolating the variables, so we need to get rid of the -1 and 2. That would mean to isolate y. Let's get rid of the -1 by moving it to the other side of the equation. So 2y equals 3 plus 1. Notice -1 was a negative number on the left. When I moved it, that negative was changed to positive. Then we have 2y equals 4, right? We're so close to isolating y, right? What else we should do in order to isolate y? There's a 2 right next to it. We need to get rid of that 2. So let's divide both sides by 2 to get rid of that 2. So now we have y equals 2, right? We wanted to solve for y, which means we wanted to isolate y. And now y is isolated by itself, and look what we have on the other side. Okay. This one, right away, people dislike the equations like this because it involves fractions. But that's precisely where we can make this equation look very linear by multiplying both sides by the same number. But before I do that, let me caution you of the most common error that I've seen people make. So this is an example of what not to do. Okay? So people who solve this, a lot of my students, on their papers, I see that they do this. They'll recognize that there are fractions here and they want to get rid of it, which is the right approach. But the way they go about doing it is not correct. So they want to get rid of this fraction here. They multiply the left-hand side by 5. So they say 5 times 6 over 5 y plus 3. And then they say, oh, I have this fraction on that side, so I'm going to multiply that by 10. Do you see what's wrong with this approach? Do you see that? It's wrong because they are multiplying both sides by different numbers. We cannot do that. Yes, our objective is to get rid of the fractions, but we can only do that by multiplying both sides by a single entity that would clear all fractions, whether you have 2 fractions, 3 fractions, 8 fractions, whatever you multiply both sides of the equation by, it must be one single term, one single entity, whatever it is, and that one entity should clear all fractions at once. Okay? So this is not correct approach. The intent is correct, which is to clear the fractions, but the way it has been implemented is not correct. We cannot multiply both sides of the equation by different numbers. So what do we do then? Well, think about what single digit that you can pick and multiply both sides of the equation by and eliminate both fractions at once. What is that number? Do you see it? If you said 10, you're absolutely correct. So 10, multiplying both sides of the equation by 10, would clear both fractions at once. And that we can do. Do you see now the difference between this and what not to do? Both sides of the equation are being multiplied by the same entity, okay, which is going to clear both fractions at once. The other thing I'm going to ask you to do is this. I do not want you to distribute and simplify at the same time. I've seen at the very least 40% of my students in each class make an error and end up with the wrong result when they combine 2 things at once, when they combine distributing the number and simplifying it at the same time. Don't do that. I'm asking you not to do that because it's prone to making error. So what am I asking you to do is distribute the number, then simplify. So break that into 2 steps, not 1. And I'm going to show you how to do that. So let's distribute the 10. I'm not going to simplify anything. So 10 times 6 over 5y plus, notice I didn't simplify, 10 times 3. Now on this side, it's already that. Still, we can distribute and not simplify. That's okay too. So 3 times, right? 3 times 10 over 10. All I did was distribute. I didn't simplify it. Now we're going to simplify. So this 5 is going to cancel with the 5 factor of 10. We're going to be left with 2, right? The 5 times 2, the 5 of the 10, factor of 10 is gone with this 5. We're left with 2. Now we can distribute. So, or we can simplify. So 2 times 6 is 12y, right? The fraction is gone. This second term, 30, the term on the right, that and that cancel each other out. We're left with 3. Again, I've mentioned this last time before. If you have 3 plus 10 over 10 or 3 minus 10 over 10, you cannot do this. You cannot do that. You can only, if you have numbers or entities added, you cannot cancel them like this. You can only, or let me give you a better example. If you have 3 plus x over x, or 3 minus x over x, can you do this? No. I don't know why people do this. You cannot cancel terms like this when you have a plus or a minus in between. You cannot do that. You can only simplify terms when they're being multiplied or divided. If you have 3x over x or something like that. If you have something like this, then you can cancel the x's and you end up with 3. This is allowed. This is allowed. Why? Because terms are being multiplied by each other. Okay, this is very, very important to remember. So here, the 10 being multiplied by 3 and the 10 in the denominator cancel each other out. We end up with 3. Now, this is a linear equation. So we can easily isolate y using what we did for the first problem. Okay, the same strategy. So we're going to get rid of the 30 by moving it to the other side. It's positive on the left. When I move it to the right, it becomes negative. So 12y equals 3 minus 30. Then 12y equals minus 27. Y, to isolate y, we need to get rid of the 12, right? So divide both sides by 12. On the left, it's easy. They cancel, the 12s cancel. We end up with y equals minus 27 over 12. Can we simplify this? Absolutely. Both 27 and 12 have factors of 3. So 27 is 3 times 9. 12 is 3 times 4, right? So the 3's cancel each other out. So we end up with y equals minus 9 over 4. Okay, I hope this is making sense. This next equation, again, I'm hoping that you have your scratch paper and you've already solved this. And you're just checking your own solutions with mine. I hope you're not just copying down what I'm writing or trying to memorize this, because that's not learning. So I'm hoping that you're working through this ahead of me. Okay, so this one, we need to isolate x. So let's move all the x terms to one side. Minus 6, I'm keeping this on this side. I'm going to bring this minus 6 to the left. It's negative on that side. When I bring it to the left, it's going to be positive x. I'm going to keep that 1 on that side. This one, I'm going to move to the other side because it's not it doesn't have the variable x in it. So it's positive on the left. When I move it to the right, it's going to be negative 1. Okay, so what do we end up with? On the left, we end up with 0. On the right, we end up with 0. So that equation is always true, which means all x values are a solution of that equation. So let me write that down. Because 0 equals 0, that means that equation is true irrespective of what value you pick for x. It's always true. Basically, these are the same entities. So, of course, they're always equal to each other. So, the equation is true, or the equation has all x values as solution, or as its solution, as solution. Okay? So this equation has infinitely many solutions. It's not like the previous example where we had one solution. This equation has infinitely many solutions. All x values as solution. Okay, sorry, let me move this like that. This one, once again, you do not want to. This is an example of what not to do. Let me use this scratch paper. So many people know that they need to clear both fractions, but the way they do it is this. This is this is an example of what not to do. So they do this. They say 9 times the left side, 8 minus 2 over 9x, and for the right side, they say 6 times 5 over 6. This is not correct because whoever does this, they are clearing the fraction by multiplying both sides of the equality by different numbers. Notice this is an equality. Let me grab my thick pen here. This is an equality. Equality means balance. There is balance on both sides of the equation. If you multiply both sides by different numbers, you will in effect destroy that balance. You are destroying that equality if you multiply each side by a different number. It does not work that way. Please do not do that. I've seen this enough. Okay? That's totally incorrect. So what you want to do is multiply both sides by a single digit that would clear both fractions in this case at the same time. Sometimes you might have 3 fractions. Then you would want to multiply both sides by a single digit that would clear all 3 fractions at once. Okay? So in this case, what do you think? What do you think is the one single digit that would clear both fractions at once? Can you think of it? It's 18, right? Let's multiply both sides by 18. So 18 times 8 minus 2 over 9x equals 18 again times 5 over 6. So that's the right way to do this. Notice both sides of the equality are multiplied by the same digit. And that same digit is going to get rid of. It's going to get rid of this fraction and that fraction at once. Okay? So what I'm asking you to do next is not distribute and simplify at the same time, but first distribute the 18, then simplify it. So break that into 2 steps. Okay, so we're going to do, this is how I would suggest that you do it. So 18 times 8, notice I'm just distributing, minus 18 times 2 over 9x equals 18 times 5 over 6. I could simplify, but I didn't, because I want to minimize the possibility of any error. Okay, now let's simplify. So 18 times 8, what is that? Is it 124 or something? Let's see. 144. 18 times 8, 144, right? When in doubt, just use the calculator. But this is still an easy number to calculate without a calculator, so it's fine. So 18 times 8 is 144. Now we've distributed, so now we need to simplify. 18 has factors 9 times 2. The 9 factor of 18 and this 9 will cancel each other out. So that 18, so this 9 goes away, we have 1. This 9 factor of 18 goes away, we have 2. 2 times 2x is equal to 4x. So we have minus 4x. Equals. Now here, the 6 goes away, we have 1. The 18 has a 6 as a factor, right? That 6 goes away, we have 3, right? 6 times 3 is 18. So that's 6, and this 6 cancel each other out. We're left with 3 factor from 18. So 3 times 5 is 15. So now the rest is really easy, right? We are solving for x, so we want to isolate x. How are we going to do that? We're going to move 144 from the left to the right. So we have minus 4x equals 15 minus 144. Right? Then minus 4x equals, that is 29, right? Minus 129. Minus 129. And then x is minus 129 over minus 4. Minus divided by minus is positive. So I'm pretty sure those two have no common factors, 129. Still, let's be sure. Oops, let me put this so you can see it. Minus 129 divided by 4, yep. So, but that's not a bad decimal number. I mean, it's not irrational, right? It's 32.25, so we can actually write that down. So you can give the answer in 2 ways. Either you can say x equals positive 129 over 4, or you can say x equals 32.25. Both of those answers are acceptable. Now on paper, both of those are acceptable, but in computer, I'm sure the online homework management system will ask you to either give the answer in exact form. If it asks you that, this is the form you want to give the answer. This is an exact form. Okay? Exact form. It's in the form of a fraction. But that has decimal in it, and if the computer program that you use for the online homework management system, I think it's MyLabMath. If that accepts decimal values, it usually says, you know, include this many decimal numbers. If it says 2, you include all of that. If it says 1, then you would have to round the 2 to 3, to 1 decimal value. Okay? Okay, so let's move to the next example. Here we have a linear equation, right? No fractions of any kind. Still, we're solving for x, which means we need to isolate all the terms that have x in them, and then that's the end of solving for x, right? Isolating x. So let's do that. I'm assuming you've done this on a piece of scratch paper. If you haven't, please pause the video, work out your own solution, and then come back to the video. Okay? So I'm counting that you've done that. So I'm going to keep all the x terms on the left and all the constants on the right. So 5x plus 3x. I have a 2x on the right. I want to bring it to the left. So minus 2x. I have a minus 4x on the right. I want to bring it to the left. So positive 4x. When we move these, they change the algebraic sign to the opposite. Equals. On the right, we just had 6, right? On the left, we have a negative 2. The only constant. So let's move it to the right. That becomes positive 2. Okay, let's combine all these things. 5x plus 3x, that's 8x. Minus 2x, that's positive 6x. Plus 4x, that's 10x. Equals 8. Right? So we're trying to isolate x. And 10 is preventing us from doing that because it's right next to it. So we need to get rid of the 10. Right? So let's divide both sides by 10. On the left, things simplify and we get 8 x. On the right, we get 8 over 10. Can we simplify this? Absolutely. Both 8 and 10 have factors of 2. Right? So 8 has factors 2 times 4. 10 has factors 2 times 5. Right? 2 times 4, 2 times 5. So this 2 and this 2 cancel out. We end up with 4 divided by 5. So that's x. Or if you like, you can, on a paper, that's acceptable to me. On either that or 4 divided by 5, 0.8. So you can also say x equals 0.8. Either this or that. In the computer, like I was saying earlier, when you complete the online homework assignments, please make sure to follow the instructions that the program gives you. If it says give the answer in exact form, that's what they're looking for, fraction form. If they ask for decimal and they say give the answer in decimal form, then that's the answer you give. Okay? This next one. I'm counting on you that you've already solved this, part F, and now you want to watch my solution. See, whenever, going back to what we said earlier, when we solve for a variable, we're isolating it. So, if we're going to isolate y cannot be part of a group. Right now, y on both sides is part of a group. Y is part of 5y plus 3 group. How do I know that's a group? The parentheses. The parentheses, the absolute value notation, the fraction line, all of these are grouping symbols. Once again, the fraction line, the parentheses, the absolute value, these are grouping symbols, as well as what they specifically do, for example, in the case of an absolute value, it makes sure, the absolute value function makes sure that at the very end, all the numbers that come out of it are positive. Okay? So besides that, absolute value itself is a grouping symbol. So if we have y cut up in a group on the left and on the right, we're not going to be able to solve for it. Because remember, solving means isolating a variable, and we cannot isolate a variable if it's part of a group. So the first thing we should do is ungroup y. How are we able to do that? We need to distribute the number in front of each parenthesis. So let's do that. So we're going to say 4 times 5y. Notice I'm distributing, not simplifying. Plus 4 times 3. That, what I just did with 4, distributing it into these terms, ungrouped y from the 3. Y on the left side is no longer grouped with this 3. Let's do the same thing on the right. Distribute the 3 into both terms. So 3 times 2y minus 3 times 5. Are you following this? I hope you are. If not, you ought to let me know with your questions. So now let's simplify. 4 times 5y, 20y, plus 12 equals 6y minus 15. Right? Now, y has been ungrouped, right? Look at it. It's no longer on the right, it's no longer grouped with negative 5. On the left, it's no longer grouped with 3. So now let's take this one step further and isolate the y terms on one side. So we have 20y. Bring this positive 6y to the left. It becomes minus 6y equals minus 15 on the right, minus 12. As we move positive 12 to the right, it becomes negative, right? Because it was positive. So 20y minus 16y, that's 14y, equals minus 27. Right? What else we have to do? Y is not isolated, right? It's got a 14 next to it. We need to get rid of this 14. So let's divide both sides by 14. So on the left, we have y, because 14 and 14 cancel out. On the right, we have minus 27 divided by 14. Can we simplify 27 and 14? Do they have a common factor? No. Right? 27 is 3 times 9. 14 is 2 times 7. So these two numbers have no common factor, so we can say this is our solution for y. Okay? Let me move this way. Okay, so now this next one. Again, please make sure you pause the video, solve this problem on your own, and then come back to the video. Okay, so once again, if we're solving for an x variable, we can't have it be part of a group because we need to isolate it. So the first thing we should do is ungroup x. How can we do that? By distributing this number in front of the parentheses into everything. So we have 2 times x minus 2 times 4 equals, 3 is by itself, 3. Now we need to distribute this minus 5. Not positive 5, minus 5. All of this gets distributed to that. So plus minus 5 times 2x plus minus 5 times 1. Are you following this? I hope you are. If not, please let me know with your questions. So let's simplify. We're done with distributing. look at x is no longer part of the group that was defined by the parentheses. X has not been isolated yet, but it's a little bit more free or freer than before. Okay, so let's simplify. 2x minus 8 equals 3. So we have minus 5 times 2x. That'll be minus 10x. In here we have minus 5 times 1, minus 5, like that. All right. So now let's move all the x terms to one side and all the constants to the other. I have a 2x on this side. Great. I'm going to move this minus 10x to the left. When I do that, this minus becomes positive, plus 10x, equals the 3, the minus 5. I have a minus 8 on this side. When I move it to the other side with the other constants, this is going to be positive, plus 8. Okay. Now let's combine these. We have 12x equals 3 plus 8 is 11, minus 5 is positive 6. Right? 11 minus 5, 6. Then we're solving for x, right? Which means we need to isolate x. Is x isolated? No. Why not? It's got a 12 next to it. We got to get rid of the 12. So 12 divide by 12. And we end up with x equals, on the left, these cancel like that. On the right, 6 over 12, right? Can we simplify this? Absolutely. 6 over 12 is 1/2. 1 over 2. Okay, like that. Okay, so next topic is zeros of a function. Zeros of a function, if you read this paragraph, which is a summary of what you find in the book, that'll be great. So the zeros of a function is any number c. I'm using, why did I use c? I'm trying to, as I was summarizing this definition, I was sticking with the language used in your textbook so that if you read these notes and you read those and compare them, they match. They don't become confusing. That's why I use those letters that your textbook uses. So for any number c, if you evaluate this function at some number c and you end up with 0, then the number c and any number like it, it could be more than one number that would make a function equal to 0, such as quadratic inequalities, right? There's always more than one number. Well, mostly, not always. Mostly more than one number that makes a quadratic function equal to 0. So there could be more than one number that achieves that. So, and that number c is called the zero of the function, because when you plug that number into the function, you get 0. Okay? So, it says, for these examples, it says, find the zeros of the following linear functions. Okay, please pause the video. Answer this question, then come back to the video. I'm assuming you've done that. So the zero of a function would have to be an x that would make this f of x equals 0. Okay, so f of x would have to be equal to 0 for us to have a zero of a function. So let me then replace f of x with 0 equals 8 plus x. Solve for x. What do we get? We get x equals negative 8. That's the zero of that function. So if you plug in for x with negative 8, you get 0. So negative x equals negative 8 is the zero of that function. How about here? Well, again, to find the 0 of a function is to find the value that would make this function equal to 0. So 0 equals 2/5 x minus 10. We have a fraction. Nobody likes fractions. Let's get rid of it. How do we get rid of this? Multiply both sides by a single digit that would clear the fraction or fractions. What would that number be in this case? It would be 5. So 5 times 0 equals 5 times 2/5x minus 10. On the left, we get 0, right? On the right, let's distribute but not simplify. So we have 5 times 2/5x minus 5 times 10. 0. 5 and 5 cancel each other, right? Like that. So we end up with 2x minus 10. So if we isolate x and solve for x here, what do we get? We get minus 2x equals minus 10. And then we get x. We're solving for x, which means we're isolating x. What is preventing x from being isolated? This minus 2. So let's divide both sides by negative 2. What do we end up with? We end up with minus 10 divided by minus 2, and x equals to minus 10 divided by minus 2. It's positive 5. So x equals 5 is the 0 of that, let's see. I might have an error here. Let me find it. Yes, I do. Let me correct this error, guys. So 5 times minus 10. So this was okay. This is 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 not okay, because this should be 50. So let me correct it with my thick pen here. Minus 50. So this would be minus 50 equals minus 50 minus 50 divided by minus 2. So this would be positive 25. X equals positive 25. Okay, and let me correct that. Like this. So x equals 25. If we plug that 25 here, and let me make this like that. 25 times 2 is 50. 50 divided by 5, 10. 10 minus 10, 0. So that's the 0 of the function. Here, we have 0 equals 3x minus 9. Let's solve for x. So we have 9 equals 3x, right? We're solving for x. So we need to get rid of this 3. How do we do that? We divide both sides by 3. Equals x. So you plug here for x with 3, you will get 0 for the function value. Okay, so x equals 3 is a 0 of that function. X equals 25 is a 0 of this function, and x equals negative 8 is a 0 of this function. So word problem solving is important because for the vast majority of you, math is not a major. You are majoring in some other field, such as chemistry, physics, economics, sociology, psychology, nursing. All of these other majors, these are have many, many real-world applications, problems that are numeric in nature. So word problem solving is helpful in just showing a few examples of how we apply mathematical equations and symbols to solving problems. Just a few examples to demonstrate how this transition is done from mathematics to other fields. As a matter of fact, this whole word problem solving is called, it's a vast field of study in its own in the departments of education. They research this, and it's called the transfer of learning. For those of you who are interested to learn more about it, you can search for transfer of learning in mathematics, which means how do we transfer what we learn in solving equations like this, which are completely mathematical in nature, to real-world situations where we have some kind of a context where we can apply equations, where we can apply inequalities, and so on. Okay? So what are the few steps to problem solving? So this is what I suggest. First thing is read the problem several times. Don't suffice with one time. If you read a problem statement once and you know exactly what you need to do, then you go ahead and do it. No question about it. But in most cases, when you see a problem for the first time, you want to read it one time just to get a feel for what is it talking about. Is it talking about biology? Is it talking about banking? Is it talking about some other context? Things in motion, trains or cars moving. What is it that it's talking about? And then, as you read the problem several times, think about any formulas or mathematical relationships between the unknowns and known quantities. This is usually, not always, given to you. So, for example, if you're talking about some money value that is being manipulated, then you are given some kind of an interest equation or interest formula, whether it's a simple interest or compound interest. There are various interest instruments, financial instruments, so you might be given the formula for that. Or some physical context. If things are in motion, then you do want to have access to what those formulas are. Even if you don't have access to, even if you don't have it, you can certainly search for it on a computer. So then take the unknown. In the first step, you get a feel for what's known and what is being asked about, right? So take the unknown and assign a variable to it. This is a very, very important step. Why am I saying this and why am I boxing it? Here is why. See, in these problems that we just did, right, the variables were given to us. The y is given to us. The x is given to us, right? The equation is given to us. So we already know what is not known, what is known. The known ones are 2, -4, 3, -5, 2, and 1, right? Any constant number that you see is given. The variable is x. And the same thing is true in this equation. The y is the variable, and the other constants are known values. That's why we see them listed there in the equation. But in a word problem, always, unless the author says pick this variable for time, let's say, if they say pick t for time, unless the author of the problem says that, in most cases, vast majority of cases, you need to assign your own variable. As a matter of fact, after each video that I prepare, I go and prepare some online homework assignments for another course. And for that course, I have to put in some word problems. So I make suggestions, okay, assign variables that are called this and that. I make those kinds of suggestions to my students, okay? So take the unknown and assign a variable to it. Very important step because it's not been given to you. So you need to introduce the variable, okay? And then using any variables that you introduce for the unknowns, translate the word problem sentence by sentence to mathematical equations. Only after you have introduced a variable of your choice, a variable that makes sense to you, you can begin to translate a problem from plain English to mathematical terms. Okay? Only after you've introduced a variable you can do that, not before that. Then solve for the unknown. Solve for the variable that you introduced. Okay? So here we have, your book does this, so I'm following what formulas they provide. So they provide a motion formula for the distance. So they say that the distance traveled by an object moving at a constant speed. This is critical. The speed should not be changing, or it should not be a variable speed. It should be a constant speed. Imagine if you drive up 95, US 95 at a constant speed of 70 miles an hour or 65 miles an hour. When you do that at that constant speed, this is when this formula applies. Your speed should, or the speed of the object or entity that is in motion should stay constant. If it does not change, then we can apply this formula. Okay? Then another formula that your book talks about is the simple interest formula. The emphasis is on simple interest, not the compound interest. The compound interest is something else. It has a totally different formula than this. Okay? So the simple interest formula earns simple interest, only earns that interest on the original amount invested. So this is for your information. Please read that on your own and make sure you understand it. It's just saying that if you invest $1,000 at 5% interest for the next 10 years, the interest that you earn annually on that $1,000 with 5% interest, it's going to be $50 every year. It's not going to change. So your money is accumulating interest, but simple interest does not change. Every year after year after year, the interest on the amount that you invested as $1,000 is still $50. So the next second year, you're going to have $1,050 in your account, right? Not 1,000, but simple interest applies to the 1,000. So you're still after the end of the second year, you're going to earn another $50. After the end of the third year, another $50. Fourth year, $50. That's simple interest. The interest only applies to the original money that you invested, not to anything that the money is accumulating. Okay, so you're not going to, with simple interest, you're not going to earn interest on interest. You're only going to, with simple interest, you're only going to earn interest on the original money that you invested. And for such an account, that's the formula. So the principal, so I stands for interest, simple interest. P stands for the principal amount deposited, which is $1,000 in this example that I gave. R is the annualized interest rate converted to decimal values. This is very important. Converted to decimal values. I say this because many times I've seen people use, if the interest is 4.8%, they just use that in their equation as 4.8. They don't bother to convert it to decimal form, which would be 0.048. Okay, so when you use this formula for R, the interest rate must be converted to decimal values. And T is time in years. So having introduced these two formulas, let's look at some word problems. Again, this is very easy to do. You have the video in your disposal, right? This video. You can watch it anytime. So I need you to give yourself the opportunity for your own mind to think. So before you watch my solution, please solve each of these word problems on your own and then watch the video, okay? And I'm counting on you that you will do that. So the average worldwide daily calories intake per person has increased from 2,200 to 2,800, right? So we're consuming more and more calories. Since the early 1960s, since that time, the average daily caloric intake per person in the United States is that much, 3,688 in the United States. Okay, so in the United States, so in the US, 3,688 calories on average consumed per day. Notice what I'm doing is just organizing what I'm reading. Okay, that's all. Then this is about 86 point, so that 3,688 is about 86.4% more than the average daily calorie intake per person in Haiti. So let's assign, and then they say find the average daily calorie intake per person in Haiti. So we need to introduce a variable. Remember when I box that, take the unknown and assign a variable to it? Very important step. If we don't assign a variable at this point, we cannot solve this problem. So the unknown is find the average daily calorie intake per person in Haiti. So let's assign a variable to it. H is equal to average daily calorie intake per person in Haiti. Okay? That's what they want us to find. That is the unknown. That is the thing we want to assign a variable to it. Okay? Very important step. So, if we're looking for this, right? So that is the unknown. Here's the question mark. What is that? What is the average daily calorie intake per person in Haiti? We are given a relationship between that variable which is not known, or the unknown, and the caloric intake per person in the United States. We are told that the caloric intake in the United States, this, is about 86.4% more than the average daily caloric intake per person in Haiti. Okay, so that is, let's translate this piece. We're going to translate from here what I've boxed in red. We're going to translate that into this equation. Watch what happened. We introduced the variable for the unknown. The last sentence. Find the average daily caloric intake per person in Haiti. Right? We introduced the variable. Then, we're going to, using that variable, we're going to translate that, what I boxed, into an equation. We couldn't do that if we didn't have the variable, so you must assign a variable first. So we have 3,688, and this is the calorie intake in the US, average, right? Average intake, calorie intake. Some people have consume less, some people consume more, but that's the average. This, we are told, this is about 86.4% more than the average daily calorie intake per person in Haiti. So the average daily calorie intake in Haiti is H. We're looking for that. Is that equal to what we consume here in the United States? No. In the United States, we consume 86.4% more than this. So plus, we got to translate that percentage to decimal. 0.864. 86.4% of what? 86.864% or 86.4% of what? Of what people in Haiti consume. So H, that's what people in Haiti consume. That's not equal to what we consume here in the United States. What we consume in the United States is equal to what people in Haiti consume plus 86.4% of this. So 0.864 of the caloric intake in Haiti. Okay, so notice that that's not true, right? What we consume in the United States is not equal to what people consume in Haiti. What people consume, the caloric intake in the United States is equal to what people in the caloric intake in Haiti, which we're looking for, plus 86.4% more than this, which is 0.864 times H. Okay, so H, we know that it's the average daily caloric intake per person in Haiti. So we solve this equation for H, and we have the answer we're looking for. Okay, so we have 3,688 equals, the coefficient here is 1, right? 1 plus 0.864 is 1.864 H. And then we're isolating H. We're solving for H, which means we're isolating it. Right now, it's not isolated because of this 1.864. So we need to divide both sides by 1.864 to isolate H. So let's calculate that. We have H equals 3,688 divided by 1.864. What do we have? We have that much. So maybe we want to round that to one decimal value. It would make sense, right? So 1,978.5. And this is, of course, the average. Oops. Like that. Okay. All right. Here we have another word problem. Please pause the video, write down your own solution, and then come back to the video after that. That's how you become really competent and proficient and confident with solving these problems. You got to give it your own shot first, guys. So I'm trusting you that you've done that. You already now have your own solution, which is great. So Kia borrowed money from her father at 5% simple interest to help pay her tuition at Wellington Community College. At the end of 1 year, she owed a total of $1,365 in principal and interest. So that includes the principal that she borrowed. Principal means what she originally borrowed from her dad. And interest. So that money includes both, the interest and the principal, the amount she borrowed. Okay, the principal is amount she borrowed. How much did she borrow? How much did she borrow? Do we need a variable for that? Absolutely. If we don't introduce a variable now, we're not going to be able to solve this problem. So let's introduce the variable. X amount that Kia borrowed. Okay, great. Now we have a variable, we can work this problem out. Kia borrowed money from her father at 5%, and that is the question mark, right? We're looking for that. We know that she borrowed this money at 5%, so the interest on that amount would be 0.05x. Interest on the amount that Kia borrowed. Notice I can do this only because we've already introduced the variable. So if you don't introduce the variable of your choice, I just picked X, you could choose anything you like. You can pick A or B, but you need to introduce your own variable. So that much, 5% of whatever she borrowed, is the interest on that amount that she borrowed, right? So we know that at the end of 1 year, she owed a total of $1,365 in principal, which is that. As a matter of fact, let me say X is the amount that Kia borrowed, i.e. the principal. Okay, I want to make sure that you guys understand what that is, the principal. How much did she borrow? Okay, so let's translate that. She owed a total of $1,365. So $103,065 should be equal to amount she borrowed plus interest, right? Isn't that what that is saying? She owed a total of $1,365 in principal and interest. That is that. So let's substitute for this with the variables that we have. 1,365 equals amount she borrowed. We took that as variable X plus interest is that much, right? 0.05x. So now we have our equations. This approach is true for all word problems. So you read the problem, you assign a variable to what is not known, and then you create relationships between what is known, which is the 5% interest, and what is not known, which is what she borrowed. We know that at the end, she paid this much to her dad. We know the interest was this over the year, but we don't know how much she borrowed. So this equation gives us a relationship between what is known and what is not known. Okay? So the rest is just algebra. 1,365 equals 1.05x. So we're solving for x. That means we need to isolate x. What is preventing x from being isolated? This 1.05, right? So divide both sides by 1.05. So we have x equals, let's see. So 1,365 divided by 1.05. $1,300 is how much she borrowed. Okay. I hope this is making sense. Again, don't look at this problem just for this problem. Look at the approach. That's what's more important than the problem itself. That you read the problem, you make a note of what is not known and what you're looking for. You assign a variable to it, and then you establish a relationship between the known and the unknown. Okay, that approach is the same for all word problems, whether you're taking an economics course, marketing course, finance course, physics course, chemistry course. That is always the same. Okay. So, Marshall, again, for this problem, please pause the video. You have access to the video no matter what, right? Give yourself the opportunity to solve this problem with your own mind. It doesn't matter if you make errors. If you don't, that would be great. But if you do, that's still great because you're still getting your own mental engine working, which is what you need to do. Then come back to the video. Okay? So, Marshall makes an investment at 4% simple interest rate. So that is the kind of interest rate that only applies to the principal, right? Remember that. At the end of 1 year, the total value of the investment is this much. How much was originally invested? So, how much was originally invested? You need to introduce a variable for this. Okay? So, for the previous problem, we assigned x. Let's assign another variable to this unknown. So after our first reading of the problem, we know the unknown is how much Marshall invested. So let's assign a variable to this, P, amount Marshall originally invested. If you don't introduce your own variable, you cannot begin to solve a problem. It is hopeless if you just try to use numbers. You've got to introduce a variable, and we just did that. So, what do we know? What are the knowns? We know that at the end of 1 year, the total value of the investment, so it was this much, right? So 1,560. It includes the original investment plus the simple interest, right? That's what they're saying. So let's substitute for what we know. 1,560, we already know that. Original investment, what was that? We don't know, it's P. So P plus simple interest, it was 4%. 4% of what? 4% of the principal. 0.04 P. The reason I say what is because many times I've seen on paper, people just write 0.04. But 0.04 of what? 4% of what? You can't talk about percentage if you mean to also talk about percentage of what value. Only then talking about percentage values makes sense. 4%. Suppose you say you have 4% in your pocket. Well, 4% of how much? 4% of $2? 4% of 200,000 bucks? 4% of $2,000? 4% of how much? So in this case, the interest the simple interest was applied to 4% of the principal. So we introduced the variable. We made note of what is known and what is not known, and we established a relationship between the knowns and the unknown. And now we can solve this. And it all began with introducing the variable here. Okay? So we have 1,560 equals 1.04p, right? Because the coefficient here is 1, right? People ask me, how did I get that? So the coefficient here is 1. That's why we don't write it. So 1p plus 0.04p. So 1 plus 0.04 is 1.04p. Okay? So we're solving for p, the principal amount that Marshall invested, which means we need to isolate p. Is p isolated? No. It's got a 1.04 next to it. So what do we do to get rid of this? Divide both sides by 1.04. So we have p equals, let's calculate that amount. $1,560 divided by 1.04, $1,500. So the original money that Marshall invested was that much. Okay? I hope this matches. Well, I hope you are working ahead of me, solving these without watching the video. And I hope after you watch the video, our answers agree. If they do, then that means that you are building proficiency in this and you're building confidence as a result, which is what this course is intending to do. Okay? Number 5. Please pause the video, go over this, read it, do what we've discussed, introduce variable to what is not known, establish relationship between known and the unknowns in the problem, and solve it. Don't spend, under no circumstances, do not spend more than 20 minutes on this. I was going to say 15, but okay, let's stretch it to 20 minutes. But don't waste your time more than. But that 15, 20 minutes that I'm asking you, really do think about the problem. And do as what we did. Introduce variable for what's not known. Establish a relationship between the unknowns and the known. And then solve it, and then come back to the video. Okay, I'm assuming you've done that. So it says a freight train leaves a station and travels due north at a speed of 60 miles per hour. Right? So let's draw a little picture for this. With problems like this, I always like to draw a picture. I mean, I'm talking about things in motion. So here is a destination, and there's a freight train that leaves this station and travels due north, at a speed of 60 miles per hour, right? So here's a train, started going toward north, and this is the freight train. Started going north at 60 miles per hour, right? 60 miles per hour. Then 1 hour later, a passenger train leaves the same station and travels due north on a parallel track at a speed of 80 miles per hour. Okay, so we have 1 hour later, and this time there's a parallel track here. There's a parallel track going north, like that, right? And a passenger train an hour after this freight train departs, an hour later, this passenger train begins to depart toward north on a parallel track. And the speed of the passenger is going at 80 miles per hour. Okay? How long will it take? They're talking about time. How long? How long will it take the passenger train to overtake the freight train? So, there's a lot going on here. I mean, that statement is packed because they're looking, they begin with how long. So they're asking for time. So this how long, they're asking for time. But at the same time, they say, take the passenger train to overtake the freight train. We know it'll happen, right? Because this is going at a much higher speed than this one, than the freight train. So at some point, the passenger train will overtake the freight train. But overtaking means what? It means that at that moment, at the moment that this passenger train overtakes the freight, at that moment, both trains have traveled the same distance. Okay? So we're just reading the problem and interpreting it so far. Now, in our earlier, we saw a formula for distance and constant speed. These are, by the way, constant speeds, right? One train is moving at 60 miles per hour, the other one is moving at 80 miles per hour. So we're dealing with constant speed. When we're dealing with constant speed, we were given this formula. Distance is equal to r, which is speed r. Again, why am I using r? Because your book uses r. Most physics books, not math books, most physics books use v for velocity. But your book uses r, so I use r. R at this speed times time. So speed times time equals distance. Once again, speed times the time of travel equals the distance traveled. Okay, so let's write that down. We know d is equal to r times t. Right? And the definitions are given earlier for d, r, and t. So, if the passenger train is to overtake the freight train, at that moment, they both have traveled the same distance. Okay? So at that point, distance traveled by the freight train is equal to distance traveled by the passenger train. Okay? So let's write that down. So for that means, let me continue based on this. So bring this formula and incorporate it here. That means speed of the freight train times time traveled by the freight train, right? I'm replacing the distance traveled by the freight train. I'm using this formula. Equals the speed of the passenger train multiplied by the time traveled by the passenger train. So overtaking, once again, means at that moment that one train overtakes the other train, both trains will have traveled the same distance, right? So distance traveled by the freight train equals distance traveled by the passenger train. So, but we know, we were told this formula earlier, right? So then let's incorporate this formula for each train. So speed of the freight train times the time of travel for the freight train equals the speed of the passenger train multiplied by the time of travel for the passenger train. Now let's plug in for what we know. We know that the freight train was going at 60 miles an hour, right? So 60 times t time of travel for the freight train as it is being taken over or overtaken by the passenger train equals the speed of the passenger train. We know it was 80 miles an hour, right? So 80 times time of travel by the passenger train. So here now we have two times here. We have one equation, two unknowns. Can we solve an equation like this? No, not by the method, by the methods that we are talking about in this course. No. So we need to, if we have two variables, one equation, then let's see if there is a way we can establish a relationship between these two variables so that we can make it into one equation, one variable. That's the goal. Is there a relationship between the time of travel for the freight train and the time of travel for the passenger train is the question. Is there a relationship? Think about it. If at the time that the passenger train takes over the freight train, let's say it's sometime here, right? The point of, let's say that line is the point of overtake. At that point, the passenger train passes or reaches the freight train. Okay? By that time, how long would have this freight train traveled? Let's say for the sake of argument, let's say 9 hours. I'm just making a guess, but that's not important. Let's say by the time this overtake happens, the freight train has traveled 9 hours, right? What would that time be for the passenger train? How long would have this train be in motion by the time the overtake takes place? If this train has traveled 9 hours, how long this passenger train must have been traveling? Is there any clue in the problem that helps us with that? Let's go back to the problem statement. A freight train leaves the station and travels due north at a speed of 60 miles per hour. 1 hour later, 1 hour later, a passenger train leaves the same station and travels due north. So, because of that statement, then at the point of overtake, if the freight train has been in motion 9 hours, how long would have the passenger train been in motion? 8 hours, right? Because the passenger train traveled at the time the freight train took off, the passenger train is still waiting at the station, boarding passengers, right? So if the freight train has been in motion 9 hours, the passenger train must have been in motion for 8 hours at the time the overtake takes place. If the freight train has been in motion 15 hours by the time of the overtake, how long would the passenger train have been in motion? 14 hours. If the freight train has been in motion for 5 hours by the time of the overtake, how long would the passenger train been in motion? 4 hours, right? Because the passenger train took off 1 hour later. So at the time of the overtake, the passenger train has been in motion 1 hour less than the duration than the freight train has been in motion. Okay? So there is a relationship between time that the freight train has been in motion and time that the passenger train has been in motion at the time of the overtake. So what is that relationship? Well, let's write it down. This TP, or the time that the passenger train has been in motion, is TF, time that the freight train has been in motion, minus 1. Just like what we talked about, right? At the time of overtake, if the freight train has been in motion for 9 hours, the passenger train must have been in motion for 8 hours. If freight train has been in motion for 6 hours, the passenger train must have been in motion for 5 hours. So that's the relationship. The time that the passenger train has been in motion is equal to the time the freight train has been in motion minus 1. Always 1 less, right? Less duration for the passenger train in having been in motion when the overtake happens. So in this top equation, let's replace T, time of travel for passenger train, or TP, with this equivalent of it. Okay? So we say 60 times T of F equals 80 times, instead of TP, T of F, TF minus 1, right? What happened here is that because of the relationship that exists between the time that the freight train has been in motion and the time that the passenger train has been in motion, we are able to reduce this equation, one equation, two unknowns, to one equation, one unknown. Okay? Which is great. Now we can solve this equation with the techniques we've learned about in this course. Okay, so distributing on the right, we have 60 TF equals 80 times TF minus 80 times 1 is minus 80, right? So let's move things around. We have 60 TF minus, and as you can see, I'm running out of space here on the paper, minus 80 TF equals minus 80. So then we have, that's minus 20 times TF equals minus 80. So TF is equal to minus 80 divided by minus 20, right? Because T, time of travel for the freight train, is what is in question. See, how long will it take the passenger train to overtake the freight train? So that'll be minus 80 divided by minus 20, so that's 4 hours. Okay? 4 hours. So that means at the time, the passenger train has been in motion for how long? If the freight train has been in motion for 4 hours, that means the passenger train must have taken it 3 hours to overtake the, it says how long will it take the passenger train to overtake the freight train. So we can convert this to, this is for the freight train. I'm trying to put the rest of this answer up here. So that's for the freight train. Thus, it must take the passenger train 3 hours to overtake the freight train. Sorry for cramming everything here in this corner, but this, what I've boxed, kind of boxed here in this corner, is the final solution, because I just noticed that they are asking for how long will it take for the passenger train to overtake the freight train. So it takes the passenger train 3 hours to overtake the freight train from the moment it starts the motion. But at that point, the freight train has been in motion for 4 hours. Okay? Okay, with that, we have wrapped up another section. And like I say, the benefit of this whole thing that we're going through, these videos, is that it gives you the opportunity to pause the video, write down your own solution, do your own thinking, and write down your own solution, and then watch these solutions. That is very important in the learning process for mathematics. Okay, you do not want to just watch this as you would watch a video, any other video. So you would want to pause repeatedly and solve these problems without seeing the solutions, and then compare your solutions with these. I hope you're doing this, and I'll keep reminding you, and I hope that you stay true to that learning process. I want you to end up not just succeed, but end up with a really top score in this class. This class is an easy class, and you should be able to do extremely well in it. There is no reason for you not to be able to do that. Okay, so for now, have a nice day, and I'll see you all next time.